Hello, Precalculus students. Next notes are on transformations. This is section 1-4 in your textbook. And the first example reads, sketch the following functions on the same set of axes. You may want to pause here and write this function down, and also have some graph paper handy. Okay, I'm going to get in and get started right away. My first function here is y equals x squared. Now I know that graph is a parabola that has its vertex at the origin. So I'm going to put a point at 0, 0. And let's think of some other points we could plug in here. If I plug 1 in there, 1 squared is 1. 2 squared would be 4. 3 squared would be 9. And likewise, negative 1 squared is 1. Negative 2 squared is 4. And negative 3 squared is also 9. So if I connect these with a smooth curve, there is the graph of that first function. Okay, now that's just the first of 5 functions. So let's get a few more in here. I'm going to get this one in red. And the function is y equals, or f of x equals x squared plus 5. Now, if I want some assistance with this, I can get out my graphing calculator. I'll notice it's the same kind of shape. It's the parabola, but this plus 5, what that ends up doing is it shifts this whole thing 1, 2, 3, 4, 5 units up. So I'm going to get those same points, just shifted 5 units up, which gives me a parabola, same exact shape, just 5 units up from that first one. This third function, y equals, or f of x equals, x plus 2 in parentheses squared. Now, adding 5 out here ended up shifting our graph up. Adding 2 in here is going to shift our graph as well, but it won't be 2 units up. Our first instinct would be that this is 2 units to the right. However, it actually ends up being 2 units to the left. Try it on your calculator, plot some points. Either way, you'll see that this is the same exact graph. Vertex 2 units to the left. Same kind of points from there. And I'll get a few points on this one. And let me sketch that parabola. It's the same exact shape as the original one, but it is shifted 2 units left. Okay, let's talk about this fourth one. Y equals, or f of x equals, negative x squared. Now this means we want to graph y equals x squared and then make all those y values negative. Well, that's going to take our original graph, and instead of plotting a point 1, comma 1, it's going to be the point 1, negative 1. And all of these original points we had, instead of being positive y values, we're now going to have negative y values. So it's taking that original graph and it's flipping it across the x-axis. Okay, we have one more in there, and it's y equals, or f of x equals 3x squared. Now, what that will do is it'll take those points we have and multiply them, those y values, by 3. So this first point we had, 1, comma 1, is now going to be 1, comma 3. Second one, 2, comma 4, is now going to be 2, comma 12. It's going to be way up here. So what this will do is it'll take our original curve. Everything will look the same, but now it's going to give it a vertical stretch. It's going to stretch it out vertically. Now that graph is kind of a mess, but this first example, the goal of this example is to demonstrate that if we understand the shape of this first graph here, we can then take and do any of these operations, add or subtract a value, make something negative, multiply by a value, and come up with the shape of a new graph. That's what transformations are all about. Coming up with a new graph of a new function based on an original graph. Sometimes this is called a parent function, because based on this parent, we can graph any of these other functions. So let's see if we can do that with a second example. Oh, before we get into the second example, let's just jot down some general rules. And again, you might want to pause here. I'm going to go rather quickly, but if you take any function and add, C stands for any number, a constant. Take any function and add a constant, that's going to shift your graph up. And if you subtract that constant, it's going to shift that graph down. So this is going to give us a vertical shift. Take any function, add or subtract some value, you'll simply shift your graph up and down. Now, if you add or subtract some value within parentheses, kind of like in the last example, it was x plus 2 in parentheses squared. Adding a value is going to give you a horizontal shift to the left, and subtracting a value will give you a horizontal shift to the right. Now, right there is a big red flag for us because we instinctively we think that adding a value is going to move it right, subtracting a value is going to move it left. So be careful with these two. That's a common mistake that students make. Making a function negative is going to give us a vertical flipped, and you might say it's a flip across the x-axis. If you actually make the x value negative, it's going to give you a horizontal flip. Oh, there we go, horizontal flip. And you might even say across the y-axis. Multiplying by a constant, multiplying by some number, we saw that in the last example, that's going to give us some kind of vertical stretch. Sometimes students see these on their calculator. For example, on the parabola on the previous page, it made it narrower. It's really not making the parabola narrower, it's really stretching it out and making it taller. It's going to look narrower. If I were to take you and stretch you out so you were 3 times as tall, you would look skinnier too. So you take that parabola, stretch it 3 times as much, and in fact, if this C value is something like a half, it's going to make it half as tall, which will make it appear wider. And last rule, if we multiply our x by some value, that's going to give you a horizontal stretch or shrink. And I'm going to say shrink here because if you were to multiply by your x value by 3, let's say, it's going to make your graph shrink 3 times as much. It's going to be a third as wide as it was before. Okay, let's see if we can apply some of these. So second example, we need to sketch some functions. Again, you may want to pause to write these down. I'm going to forge ahead. Our first function, f of x or y equals the absolute value of x. Now our absolute value function has a vertex at the origin. And then let's just think of some points. Absolute value of 1 is 1. Absolute value of 2 is 2, 3, 3, 4, 4. Absolute value of negative 1 is 1. Negative 2 is 2. What this function, the graph of this function looks like, it's going to be a V shape. So there is your parent function. Absolute value of y equals absolute value of x looks like this V shape. Now, without thinking of points, without trying to graph, without pulling out our calculators, we can use these transformations to sketch these other graphs. So this second one, f of x or y equals the absolute value of x minus 3. So we're taking our function, subtracting 3. Thinking about what was on the previous page, that means we're going to take that function and shift it down 3 units. So it's going to be that same V shape. We're just going to be shifted down 3 units. Okay, third function, f of x or y equals x minus 7, absolute value of x minus 7. Now, since the minus 7 is within the absolute value, it's like saying it's within the parentheses. This is going to give us a horizontal shift. Careful, the mistake people make is they say, hey, this moves left 7. Actually, this is going to move to the right 7. So it's that same V shape as the original parent function. It's just moved to the right 7 units. And the last one up here, actually there's 2 transformations here. There's a negative in front and there's a 1/2. So the negative is going to flip this vertically, flip it across the x-axis. The half is going to make it half as tall. Okay, so instead of saying the point 1 comma 1 or even 1 negative 1, it's going to be 1 comma negative 1/2. So we're going to have that V flipped across the x-axis, and it's going to be half as tall. So it's going to appear, let me get this right here, appear wider but really it's just half as tall as that original function. Okay, so if you know your transformations well, we don't need to know how to graph every little thing that's going on here. We just need to know these parent functions. Once you know the graphs of these parent functions, all these transformations are always going to be the same, and the rules, what happens is always going to work the same way. Now here's something else we can do with those. Let's say we have a more complex looking function, such as this. Well, if you look at this, this is really just a combination of the transformations we had on the previous page. We know y equals the absolute value of x has this V shape with a vertex at the origin. So let's apply all those transformations to this. So we know, and I'm going to start with the x, we know the minus 7 is going to move this thing 7 units to the right. So here's my original vertex. 1, 2, 3, 4, 5, 6, 7 units to the, did I say left? 7 units to the right is going to be our new vertex. The negative 1/2 is going to flip the v, so it's not opening upward, it's opening downward. And the half is going to make it half as tall. Minus 3 is going to shift that 1, 2, 3 units down. So here's my new vertex. My graph is going to be wider, opening downward because of the negative, and there's the graph of this function. So by knowing transformations, we don't have to plot points. We don't need to pull out our calculator. We don't have to do anything real complex because we know minus 7 moves it right 7. 1/2 makes it half as tall. Negative flips it vertically, and minus 3 shifts it 3 units down. These rules, these same things are going to come up throughout the year, so the more we make use of them, the easier our work is going to be. Okay, let's take a look at another example of this. Let's try this one out, and I would suggest even maybe pausing the video at this point and trying this one on your own. I'm going to jump right in and get this done. So our parent function would be this, y equals x squared. Y equals x squared we know is a parabola with vertex at the origin. So our graph is going to be based on this. So I'm just going to put a point here at the origin. There's my reference point for this parabola. Let's see what these transformations do. And people always ask about order of operations. What should we do first? The minus 5, the 2, the plus 3? Start with your x and think about what you would do to that x. We're taking our x, we're adding 3, squaring it, multiplying by 2, subtracting 5. Go in that order. So we're taking our x plus 3. Adding 3 within the parentheses is going to move that reference point 1, 2, 3 units to the left. So there's our new vertex. 2 outside is going to make it twice as tall. So we're going to have a parabola opening upward, but it's going to be twice as tall, which is going to make it appear thinner. Minus 5 is going to move that reference point, that vertex 1, 2, 3, 4, 5 units down. So there's our vertex. This is going to be twice as tall. So sometimes to graph a parabola, we go right 1, up 1, left 1, up 1. We can go right 2, up 2 for this one. And we've got this parabola. It's going to be narrow because it is stretched out twice as tall. And there's your graph of this function. So again, we can sketch a graph of this without doing a whole lot of mathematical work because we know what these transformations will do to our graph. So just knowing your parent function and the rules for the transformations will allow you to graph just about anything. Okay, one last example, and I'm going to have you put a star in the margin right away because I will guarantee you're going to see a problem like this on your next test. The reason I'm putting this problem on your next test is because we cannot do this problem with our calculator. So many people rely on their calculators to do these transformations for them. In this case, it won't work. Here's why. I'm giving you some graph of some function. We do not know the equation of that function. We just know here's f of x right here. Looks like this. It's this curve shape that goes upward, then downward, then upward. Okay? Based on the graph of that function, what would it look like if we graphed this new function? Now, if you know your rules of transformations, this problem is not bad. If you don't know those, if you pick up your calculator here, you'll find it does you no good. Okay, let's think about the rules. So start with your x. See this minus 3? We know a minus 3 in the parentheses is going to move our function to the right 3. We know this negative out in front is going to flip the function vertically. We know that adding 5 out here is going to move this function up 5. So we know what we need to do to this graph. Our calculator won't help us because we don't have the original equation. So we need to pick a reference point. So I'm going to pick right here at the origin. There's our reference point. First, let's move that reference point 3 units to the right. Second, we know our graph's going to be flipped vertically. So instead of going up, down, up, it's going to come this way, down, up, down. Now, from this point, we know it's going to go up 5 units. So 1, 2, 3, 4, 5 units up. Here is our new reference point. Now, this is kind of tricky sometimes. Instead of going up, down, up, I'm going to start up here and come down, up, down. So let's try to do that. So I'm going to come here down, up, and down. So it's the same exact shape. It's shifted right, it's shifted up, it's flipped vertically, and there's our new function. If you know the transformations, this is not a difficult problem. If you rely on your calculator, this problem is impossible. There is no way to do this on your calculator. Okay, that wraps up your notes for this section. We know we have an assignment to take a look at, so please work on that and then hit the next set of notes.